So now we're ready to talk about some special cases, probably more correctly stated, some special outcomes. In example 3 in the notes, you can see that you're given a 3x3 linear system. I went ahead and I've augmented it. And then I've actually went ahead and simplified it down. Now I don't have any of the work, but as you can see, using the elementary row operations, we end up with this thing right here. Which might, to be a surprise, is not our goal matrix. Now, obviously we'd like to hit our goal matrix, but sometimes we're prevented from that. Now, it's up to us, though, if prevented from hitting our goal matrix, to interpret the results. And if you understand what I had been writing at the end of each problem in green in the previous videos, then this won't be very difficult for you either. So what I want to point out is if you were to take these numbers out of its matrix form and go back into things with x's and y's, this very last step here would say 0x plus 0y plus 0z equals 1. In other words, 0 equals 1. Well, that's clearly not true. So because we hit a false statement, we're absolutely to the point where we can say that there is no solution to the 3x3 linear system that we originally started with, the one that gave us this augmented matrix. Okay, so similar to the last one, we went ahead and I augmented the given matrix using elementary row operations. This thing actually simplifies down to what I have there at the bottom. Now, again, just interpret it in terms of x's, y's, and z's. This bottom one says that 0 equals 0, or the middle one says 0 equals 0, but the bottom one also says 0 equals 0. So similar to the last one where we had a contradiction, now we actually have everything fall apart, but we're left with a true statement, which is going to imply infinitely many solutions. Now, it is up to us to figure out what the infinitely many solutions are, and this is really important. Notice how we have 2 rows of zeros. 2 rows of zeros means something different than having 1 row of zeros. So let's handle the case that we have in front of us where we have 2 rows of zeros, which does imply infinitely many solutions. So this is the case where if you go back and you look at the original system that's given, the one that gave us this matrix when we augmented it, the one that you see in your notes, those 3 equations, if you look carefully, are all 3 the exact same. If you take the first one and you divide it by 2, if you take the last one and you multiply it by a -1, all 3 of those will end up being equal. And so the solutions we have here would be written as all x, y, z ordered triples such that 2x minus y plus 3z equals 2. So all ordered triples will work provided they satisfy the given equation of that plane. So you do have infinitely many solutions, and we were very careful to specify precisely what they are. Now let's look at the case where we have just 1 row of zeros come out. Okay, so once again, example 5 here starts with our augmented matrix of the 3x3 system given in your notes. Elementary row operations takes us down to this form here. And very similarly, we can see now our 0 equals 0 statement is true, but as I pointed out before, is only 1 row. We still have 2 other rows that we were forced to deal with. Now, true statements do imply infinitely many solutions, but for equations and systems of planes, we have some other possibilities. What we're looking at here is actually 3 planes intersecting at a line. So they intersect at a line, and the line has infinitely many points. So now what we have to do is figure out a way to represent that line, which would take into account all of our solutions. So I would suggest the moment you get to this point, you realize there's infinitely many solutions, you have 1 row of zeros, I would go back into its x, y, and z form. The first line says x equals -2/3. The second one says that y plus z equals 7/3. And the last one is just all zeros. So your template here will be something like this, where you have 4 things to fill in. This is your x, this is your y, and this is your z. Out of those 3 coordinates, you're allowed 1 variable. Now for us, it's pretty clear as to what x would be. X is going to end up being negative 2/3. It has to be. The y, on the other hand, if I solve this, I get 7/3 minus z. If I plug this in, I've elected to use the variable z, and you're only allowed 1, which means the variable needs to be itself. So if we've elected to use z, then z has to go there, and z can be any real number. And this is a way of presenting the line of intersection dependent only upon one variable, z. Now, this is a perfectly fine answer, but to take it maybe a step further, I'll come down here. It's not the only answer. We do have a few choices when it comes to putting these together. We still need to make sure our x is negative 2/3. But now I could have solved this differently. I could have said z equals 7/3 minus y. And if that's the case, then my z will be 7/3 minus y, and I've elected to use y as my variable. So then the y needs to be itself, and y can be any real number. So both of these answers are perfectly fine, perfectly acceptable. You just got to make sure that you're only using 1 variable in all of them, and you have to remember that this is the line of intersection of all 3 of these planes. So in this last special case, what you should notice, hopefully, is that you only have 2 equations now. So we're essentially being asked, where do these 2 planes intersect? And if you think about it, the answer can't be at a point. They cannot intersect at a single point, so you really only have 2 possible options. You have no solution, or you have infinitely many solutions. So even simplifying this down using our row operations into our goal form isn't really done the same way. So you want to make sure that you're able to get your 1, 0, 0, 1, but from there, knowing that there's either going to be infinitely many solutions or no solutions, you don't really have to worry about anything else. Once you simplify it into this form, go ahead and come out of matrix form and go back into the standard form with x's and y's. So we'd have an x plus a z equals 0 and a y equals 2. We're ready to put this thing together now in a similar way as the last problem. I know that x can equal negative z, so there's our negative z. Our y has to equal 2, and our z needs to be itself, assuming z is a real number. So once again, we're not really hitting the goal matrix here, but that's because we have some added insight as to what our outcome should be before we even get started. So we want to make sure we get our 1, 0, 0, 1 like we did. Whatever's left is left. Go back into your standard form and then put your solution together similar to what we did in the last problem.